Okay, via request from one of your classmates, I'm going to go ahead and record a video going through the solutions for the final exam that we took last week. I'll try to be brief. There's a lot of questions, so if I go into full level of detail, this video could be 2.5 or 3 hours, which I don't think anybody wants to sit through. So I'll give you the quick solutions, and again, if there's anything that's unclear, feel free to contact me. Again, this is mostly for closure. Obviously, the course is over, but some people might find it helpful to go over things and see where they may have gone wrong on the final exam. Okay, so let's go into the first one. The first question here, it asks about some questions about these molecules, mostly point group or other things related to their symmetry. And so this first one here is a conjugated organic molecule, planar aromatic system, and we want to find the point group first. And so if we look at this molecule, there is a C2 axis that goes right through the center there. So it would rotate these two nitrogens onto each other, or the corresponding rings onto each other on each side. So it does have a C2 axis, but there is not a perpendicular C2. If we try to do a C2, for example, that's vertical like that, what we would find is that there is no symmetry operation that exists with that axis. It changes the position of the two nitrogen atoms. So we have only one C2 axis, so it would be a C2 point group, and then the molecule is planar, so perpendicular to that C2 axis is a reflection plane. So that gives us C2H as the point group. Now, to identify if it's centrosymmetric, we just need to figure out if there's an inversion center or not. So you can either look at the character table for C2H, or if you weren't confident that you got the point group right, just search for the inversion center itself. And there is indeed an inversion center, again, right at the middle of the molecule. Nitrogens invert onto each other, corresponding parts of each ring invert onto each other, so this would be centrosymmetric, and the C2H point group does include inversion as one of its operations. And then for chirality, it needs to lack an improper rotation axis. Well, remember that sigma is equivalent to S1, inversion is equivalent to S2, so the C2H point group includes two improper rotation operations, even though they're not labeled as such. So any planar molecule is going to be achiral because of the reflection plane anyway, so that would be a no for that one. The next molecules that we had were coordination compounds. So the first one is this iron 3 tris-acac compound. I guess I gave away one of the answers already. But first thing we asked for is iron oxidation state. So we have, in this molecule, we have overall charge neutral, so the total charge is 0. We have 3 minus 1 ligands, and then we have plus 3 on the metal to add up the charges all to be 0. So our iron oxidation has to be plus 3 for the overall complex to be neutral. Now if we have plus 3 for iron, I'm not going to go to the periodic table here, but you should know as an inorganic chemist finishing your first semester of graduate school now, for most of you, that iron is in group 8. So that means iron on its own has 8 valence electrons, but we're taking away 3 of those for the plus 3 oxidation states. There should be 5. That should have been d electron count. Sorry about that. I mislabeled that on this. So we're looking for d electron count there. We already found the oxidation state. So the d electron count is 5 because iron is group 8, but there's a plus 3 oxidation state, so we lose 3 of those. And then the highest order of proper rotation, we didn't ask for the full point group here, but if we notice that right through the middle here, there is a C3 axis that rotates the oxygens onto each other in the front from the 3-acax, as well as the ones in the rear that are shown here, like that. Okay, so there's a C3 axis that interchanges the 3, and that's going to be your highest order. This would actually be the D3 point groups. There's also some perpendicular C2s in there, but C3 would be the point group, or sorry, the highest order rotation. All right, last one here is this iron compound. So first we did ask for the point group. So this molecule again is drawn as being roughly planar, or we would assume that's the case without any further information. We have a C2 axis that goes there. It rotates the whole thing like that. But in this case, we also have perpendicular C2 that would flip the molecule like a pancake as I've drawn it in the board. And the other one that goes horizontally as well. So you only have to find one of those two perpendicular C2s, identify that this is going to be a dihedral point group D2. And again, there's reflection planes that are perpendicular to each of these rotation axes, horizontal and vertical and perpendicular axis. So that makes it a D2H point group. All right, and then the oxidation state for iron. This one was a little bit more challenging to get. So when you have a coordination compound that involves, there's basically 4 different parts to it. So we told you that N2 was in its 2- form. We also told you that the ligands, these chelating ligands, are each 1-. We call those NAC. So those are 2 times -1. And then we have 2 other metals, potassium and iron. So for the potassium, we have to recall that in any sort of coordination compound or ionic compound, potassium should have a +1 charge based on its location in the periodic table. So then what's that we're left with is overall charge neutral, no net charge, but we have a 2- charge from the nitrogen ligand, 2 1- charges from the NAC, 2 +1 charges from the potassium, and then whatever iron would be to balance out to 0. So in this case, we have -4 from the ligands, +2 from potassium, leaves a total of, we need a +2 charge for iron. So 2 irons have a total charge of +2, but we're looking for the oxidation state on each iron, which would be +1. So each one has to have a +1 charge for all the charges to balance to 0. That's the only one we don't know when we have the ligands and the 2 potassium ions. And then finally, for centrosymmetry, again, we look for the inversion center, or we look at the D2H character table. We find that there's an inversion center, so this would be centrosymmetric. Again, right as at the middle that I've drawn, that little dot there is where the inversion center would be. All right, the next question here was pretty straightforward. I would say most of us did really well on this one, just using angular overlap models to parameterize the d orbital energies in terms of E sigma and E pi for a square pyramidal fragment. So just an octahedral compound where we've removed one of the ligands to leave a square-based pyramid. So for that, we need the angular overlap table, which I reproduced here. It was in the supporting information I gave you. We're looking at a square pyramidal structure, so we need positions 1 through 5. So we only really need to consider this part of the table here that I'm going to box in as best I can. The rest of this doesn't really matter, so we just need those positions there. So if we go through the 5 d orbitals, then what we will find is that all of them are either sigma only or pi only. There are no d orbitals that have mixed sigma and pi character. So for dz squared, what we get is 1 plus 4 quarters. That's a total of 2 for E sigma and 0 for E pi. If we go to dx squared minus y squared, that's another one that only has sigma interactions. So this time we have 4 times 3 quarters, which is a total of 3 for E sigma, 0 for E pi. And then the rest of the 3 d orbitals, xe, yz, and xy, just like they do in an octahedral situation, we're just removing one ligand from the octahedron. They're going to have only pi interactions. So xe is going to be 1, 2, 3 E pi's and 0 E sigma. Yz is going to be 1, 2, 3 E pi's and 0 E sigma. And then xy is going to be 1, 2, 3, 4 E pi's with 0 E sigma. So this one was fairly straightforward because there weren't really any fractions to deal with, and everything was either sigma or pi. So it's very similar to the octahedral case, but by removing one ligand from the z-axis, we reduce the E sigma character for dz squared by 1, and we reduce the E pi character for xz and yz by 1 as well, otherwise identical to octahedral. So with that, we're going to be able to then do a d orbital splitting diagram. So what we asked you for here was to label the Mulliken symbols and the orbital parentages, and also to populate with the correct number of electrons. So this is going to be WCO5. So the first thing we do is, if we look back at the angular overlap model, we know that the ones with E pi are going to be lower energy. E pi is smaller than E sigma. Moreover, these are pi acceptor ligands. CO is a pi acceptor, so E pi is actually a negative number in this case. So the one that's going to be the lowest energy is going to be the one here for dxy, 4 E pi, and again, in this case, E pi is negative because it's a pi acceptor. So that's going to be lowest energy, followed by xz and yz. So when we're labeling this, there's different ways you can think about this, but we want to have dxy at the bottom because it has only pi interactions with the ligands, and then xz and yz next. they have pi interactions, but there are less of them, and pi interactions in this case are stabilizing. Now, in terms of the Mulligan symbols for each of those, that comes right from the character table. So dxy here is b2, and then xz and yz transform together as e, which is why those two are shown at the same energy level. And the Agro model confirms that. Now, the other two orbitals were the ones that had the sigma interaction. Sigma is always going to be destabilizing. E sigma is always positive. So x squared minus y squared is 3 e sigma, dz squared is 2 e sigma, and so that means dz squared would come first, and then dx squared minus y squared as we go up in energy. Okay, so we're going to have dz squared here. We've removed the ligand from the z-axis. That's one that's going to be a little bit lower in energy now. And the Mulligan symbol for z squared is there as a1. Highest energy is dx squared minus y squared for the full 4 e sigma. And that's going to be a Mulligan symbol of, there we go, x squared minus y squared, which is b1. Okay. Now the next part of this that we graded on was going to be giving the correct number of electrons in a low spin configuration. Alright, so WCO5, tungsten is in the zero oxidation state. The ligands are uncharged for CO. So it's going to be a group 6 metal, so we should have 6 valence electrons. So if we want to lane 6 electrons low spin, we go 1, 2, 3, 4, 5, 6. We don't want to populate the higher energy levels. We want to maintain the lowest spin possible. So all 6 electrons are paired. The ground state is closed shell, and so we have no net spin, no unpaired electrons, so S would be 0. So that was the last part of this, was looking at your diagram and deciding what the spin value was. Now, I did give you credit as long as your spin value was consistent with your diagram, but it should be low spin as we specified, and that gives you S equals 0 for a D6 configuration. Alright, now the next part of this is going to be to use group theory to determine the sigma and pi selfs for tungsten pentacarbonyl fragment. So this approach here, which has us do the sigma representation first, and then multiply by x, y, and z to get the combined sigma and pi, is going to be the most straightforward. So this is going to, we'll start with gamma sigma, which is really just the representation for how many ligands are unmoved under each symmetry operation. So what we're doing for gamma sigma, I should have drawn the structure again, we're going to put a sigma orbital on each carbon, which we can label as a vector or just as a generic sigma orbital like that. So there's a set of 5 of those, and for gamma sigma, whichever ones don't move contribute to the character, whichever ones move. So for identity, there's 5 orbitals, so we're going to get character of 5 for that. For the C4 operation, I should have drawn it here. Try to draw it a little bit here so it can get easier. All right, for C4, we have 1 ligand along the axis that's not going to move, the other 4 are going to move, so we get a character of 1 for that. C2 shares that C4 axis, so same story there. Sigma V, we said, define as the reflection plane that contains 3 CO ligands. That would be, for example, this plane here that contains all 3 of those. And so we'd have 3 sigma orbitals in that plane for a character of 3, whereas for sigma D, what we're going to have is a reflection plane that cuts between the CO ligands, so only one of those would be in the plane. So those are the characters that we get for gamma sigma. And then for gamma XYZ, we have to look at, that's again the characters for the XYZ representation, one on each atom, which represents the sigma and the pi orbitals. And so gamma XYZ we have to get by looking at the character table. In the C4V point group, X, Y, and Z don't transform together, so it's going to be 2 representations added together, E plus A1. So the characters would be 3, 0 plus 1 is 1, minus 1, 1, 1. Alright, so again, that XYZ is going to be A1 plus E for this point group, which comes out to 3, 1, minus 1, plus 1, plus 1. We add those 2 representations together, and then the product of those gives us sigma and pi together. So 5 times 3 is 15, 1 times 1 is 1, 1 times minus 1 is minus 1, 3 and 1. And so now what we have to do then is just reduce the representations for this. And so what we get is, when we reduce the representation for gamma sigma first by itself, we get 2a1 plus b1 plus e. Now I didn't ask for this on the exam, but as an intermediate step, the best way to do this would be then to reduce the sigma plus pi representation, which gives you the multiple symbols for all of the sigma and pi cells. So when we reduce this, what we should get is 3a1 plus a2 plus 2b1 plus b2 plus 4e, if I did that correct. So let's see this. 8, 9, 11, 12, 15, so that's consistent. So those are the representations we get when we reduce this bottom line here, sigma plus pi. And then from there to get gamma pi, again, we did not ask for this on the exam, this is just an intermediate step here. But then when we, to get gamma pi, we just basically subtract the sigma from the combined. So we had 3 A1s combined, 2 of those are from gamma sigma, so that leaves us with 1A1. A2 is not in sigma, so that's going to be only pi. 2 B1s, we had 1 B1 from the sigma, so that leaves us with 1 B1 for pi. B2 is only present in the combined representations, so that's going to be 1 over pi. And then we had 4 E's from here, only 1 E from gamma sigma, so that leaves 3 for the gamma pi. So again, that one we just do by subtraction. You could also subtract the characters and then reduce. But nonetheless, that's going to be the way that we would get it. Alright, and then same problem here. This one actually ends up having some pretty similar characteristics as the last one. We're going to talk about some of the vibrational spectra or vibrational modes of this molecule. So first what we want to do is look for representation for all 3n molecular motions of WCO5, gamma 3n. We didn't ask you to reduce it, or we didn't ask you to pick out the normal modes from that, but we went ahead and just asked for the characters filling out this table here. So this follows the general approach that we use for normal modes. Now the first thing to recognize is here we're looking for all of the normal modes. We have to consider all of the atoms in the molecule. So again, this is WCO5. So we have a CO in each of those 5 positions. Alright, so the first thing we do is this one that we abbreviate here as Ni, which is the number of unmoved atoms. So the total number of atoms in the structure, we have a tungsten at the center, and we have 5 carbonyls. So the total of 11 atoms. Or in other words, N equals 11 if you're talking about the 3n minus 6 rule that we use for vibrational modes. So we're going to have 11 atoms total, so this can be a character for identity. For the C4 operation, 3 of those are along the axis. We get a character of 3 there. C2 shares that axis, so 3 of those would be unmoved under C2. As we defined before, sigma V is going to be the reflection plane that contains 3 CO ligands. So it would be, for example, this plane here, which has 3 COs. That's going to be a total of 7 atoms, 6 from the COs plus the center atom tungsten. So we have 7 from sigma V. And then for sigma D, that's going to be one that cuts in between COs. So the only ones that are in that plane are the tungsten and the axial CO. So 3 of the atoms are unmoved under sigma D. For this, we're going to use the same XYZ representation that we used in the previous one. So if we did that correctly up there, we don't have to do any more work. We just copy this directly down. So remember, when we find normal modes, it's the number of unmoved atoms, it's XYZ, which is the representations for those coordinates, and then we multiply the 2. So we get 3, 1, minus 1, plus 1, plus 1. And again, that comes from the character table, just adding up those 2 set of characters. And then multiplication gives us gamma 3n. So 11 times 3 is 33. 3 minus 3, 7, 3. So some of you, good number of you made mistakes in the first row, especially some of you in the second row, but I think all of you recognize that we just had to multiply the 2 to get gamma 3n, and so that would be how we would approach that one. Now, the next one, though, dealt with just the CO stretching modes. This is actually going to look identical to gamma sigma as we did before, as it turns out. So if you had recognized that, you could have saved yourself some time here. But what we have is for the CO stretching modes, again, we're going to represent this as a stretching vector on each of the CO ligands. And we're just going to derive a representation for those five vectors, for those 5 stretching motions of the CO ligands only. So there's 5 of them, so identity is going to be 5. Again, C4 goes through the apical one, so one of those is going to not move under that. Same for C2, which shares that same axis. Sigma V contains 3 of them, so we have a character of 3 there, and I messed up here, there should not be a 2 there. Sigma D contains 1 of them, so there should be a 1 there. So when we reduce that, we get the same thing that we got for gamma sigma, 2A1 plus B1 plus E. It's really a representation that's very similar in terms of the vectors. They're just representing different things. All right, so we have those 5 modes, and they transform under those representations. And then to find the IR active modes and the Raman active modes, you have to go back to the character table. So IR active modes are going to transform as X, Y, or Z. As we've already determined, X, Y, and Z on the character table for C4V transform as A1 and E. Again, to verify that, go back up to the character table. Z is A1, X and Y are E. So any mode that has A1 or E representation will be IR active. That's the selection modes for infrared. So 2 of our A1 modes both of our A1 modes and our E mode are going to be IR active. Most of you just put A1 plus E. Technically it should have been 2 A1s because there are 2 A1 IR active modes, but I didn't count off for that, but that's the correct way to write that. And then for the Raman active modes, that's going to be the quadratic functions x squared, y squared, z squared, xc, yz, etc. And so if we go to the character table for C4V, we have quadratic functions in all the representations except for A2, but there are no A2 normal modes for the CO stretching, so it's just going to be all of them are Raman active. So 2A1 plus B1 plus E, or you could have just said all of them are Raman active. Okay, there is no A2 mode, so if you wrote A2 there, that would not be correct. A2 is not Raman active anyway, but the rest of the 3 modes are all Raman. And there's also no B2 modes, so you have to only count modes that are actually present, but all of the ones that are present are Raman active. Alright, the next problems deal with this platinum acetylide compound that we introduced on the second exam, and there were a number of problems on this one that a lot of you had trouble with. So we brought it back on the final exam, but slightly different mode of questioning, different things we were asking about. So I gave you the structure with coordinates embedded, and also gave you an approximate d orbital splitting diagram for this. So the first question is, what is the ground state term symbol? Well, this molecule is closed shell. And again, we can easily see that from the orbital diagram, which shows that all the d orbitals that are filled are doubly occupied. There's no unpaired electrons. So anytime you have a closed shell ground state, it's going to be totally symmetric. And of course, the spin would be 0 because there's no unpaired electrons, meaning that 2s plus 1 equals 1 is a single state. So it's going to be a single state, and then the term symbol is going to be whatever the totally symmetric representation is for that point group. I told you directly that it's D2H, so the totally symmetric representation of D2H is AG. Somebody put A1G, which I did take off for because there is no A1G representation in D2H, but it should be totally symmetric, and it needs to include a spin multiplicity and a mulligan symbol. Again, if you left off one or both of those, you would be points would have been taken off. Alright, so that's the ground state term symbol. Now the next thing we ask about is orbital symmetry, where we gave you the south or the molecular orbital and asked you for the mulligan symbol. Now I did have a small typo on the exam. I wrote this as B3G, but this would actually be B2G. That was my mistake. So if you wrote, for one of them, the correct answer is B2G, but if you wrote B3G because I indicated that could be one of the choices, then I didn't count off for that. So I counted B2G or B3G. I'll point that out again when I get to it. But for these orbitals in D2H, we're just distinguishing B1G G, B2U, B2G, B1U. So B1 versus B2 or G versus U. So we don't have to look at all the operations. Remember, when we apply an operation to an orbital, if orbital stays the same sign, that means the character is +1 for that operation. If the orbital changes sign, that means the character is -1. So to distinguish B1 from B2 or any of the representations, what we first can look at are the 3 rotation operations. So we have Z, Y, and X written in that order on the character table. And we define C2Z as perpendicular here. So for this first orbital here, if we do a C2Z, we're going to rotate black onto white or white onto black, so we should get a character of -1 for that. For C2Y, which is vertical, and that one we're going to rotate black onto black, white onto white, and so that gives a +1 character for that. And then for C2X, we're going to rotate black onto white, white onto black, so we should get a -1 for that. And then finally, for inversion for this, we have to distinguish G from U by looking at the inversion operation. If we put inversion center right at the middle, black inverts onto white, or shaded inverts onto unshaded, shaded inverts onto unshaded, and vice versa. So this should be a U representation because it has -1 character for inversion. But the combination of -1, +1, -1 identifies it as B2. So for those 3 rotations, Y, Z, Y, X, -1, +1, -1 is B2. And furthermore, we said that it's unsymmetric with respect to inversions. That makes it B2U. Alright, we're going to do the same thing for this one here. We notice that the orbital phase is different here, but it's still in the XY plane. So we're going to look at, we could also look at reflection operations. You could have done the XZ, YZ, XY reflections as well. I like rotations a little bit better, but sort of personal preference more than anything. So for this one here, if we look at C2Z, we're going to go black onto black or white onto white. So that should be +1 for C2Z. For Y, we're going to have shaded onto unshaded, black onto white, white onto black, so that's -1. And then for X, which is horizontal, black onto white, white onto black, -1. This one, if we go through the inversion center, we're going to invert the same phase onto itself, so we get a +1, which means this one should have a G subscript. So +1, -1, -1, if we go back to the character table, is B1, 1, -1, -1 for those 3 operations. And we just said it's G because it's symmetric for inversion. So this one would be B1G. Alright, the next 2 here are perpendicular, so maybe a little bit more difficult to deal with. But same approach, and we did give you the side view to hopefully help you out with interpreting those. So here we're just showing the top lobe of each p orbital. Side view is going to show it a little bit more clearly, but with a rotated perspective. And so for this one here, again, we can do the same 3 operations, Z, Y, X rotations, along with the inversion to identify G from U. So if we do the C2Z, we're going to rotate shaded onto unshaded, so that would be +1. For Y, what we're going to do is, if we flip this whole thing over, this shaded lobe on the top is going to rotate to the bottom under C2Y, and so that's going to change the phase. You see that also here. We'll rotate on a shaded lobe on an unshaded lobe. So it's going to be -1 for Y. And then for X, for along the axis here, when we flip the whole thing over, all of the lobes on the bottom rotate up to the top, meaning that we're flipping the sign. So it's going to be -1 as well. And then in terms of inversion, inversion is probably easier to see from the side view here. As we go through the inversion center, we invert opposite phases onto each other. So that's going to also be a U1. So we have 1, -1, -1. Which, as we said, is B1, but this time it's going to be B1U because of the asymmetry with respect to inversion. So this one's our B1U. Alright, and then this last one here is one where I counted 2 answers because of the small typo that I made. So here we're also talking about perpendicular orbitals. If we do C2Z this time, we're going to rotate opposite phases onto each other. So that would be -1 for C2Z. For C2Y, which is vertical, when we flip this, we're going to take this shaded lobe that's on the top and flip it to the bottom onto another shaded lobe. Flip those two onto each other. And so that's going to be +1 for Y. And then for X, when we flip the whole thing over along the X-axis, we're going to invert the phases. Flip that white onto black, white onto black, and so on. So we get a -1 for X. And then for the inversion operation, again, easier to see on the second view here, we invert shaded onto shaded, same phase onto the same phase, unshaded onto unshaded. So that's +1, which is G. So this is 1, 1, -1, and G. Oh no, did I screw this up? -1, 1, -1, sorry. -1, 1, -1, which is B2. And this time it's B2G because of inversion being also +1. So again, B2G was the correct answer for this, although I accepted B3G because of the typo I made in the question text. Alright, so again, that's just applying a subset of operations to distinguish B1 from B2, and then the inversion center allows us to easily distinguish G from U. Here we're talking about electronic transitions involving those orbitals. And so what we're going to look at for this one is first we have B1G to AG. Now as we're indicating here, both of these are d orbitals. So if we go to the diagram, that would be B1G to AG, that would be this transition here. But they're both d orbitals, xy to x squared minus y squared. Alright, so they're both d orbitals, which means this is clearly a dd transition if it involves only d orbitals. And then we ask for the term symbol and the electric dipole selection rule. Now we're only looking for the term symbol for the spin allowed excited state. So we only have to consider singlet states because this is a singlet ground state. To get the term symbol, we just take direct product of B1G times AG, which is B1G. It's totally symmetric, so it doesn't change it. So it's going to be a B1G with a singlet spin multiplicity for our term symbol. And then if we go to the character table, we look to see if it has, to follow the electric dipole selection rule, it has to transform as x, y, or z. And if we look at the character table for D2H, B1G does not include any of the Cartesian functions. Those are all going to be U down here. Okay, so we have, this one's going to be electric dipole forbidden because B1G does not transform as a Cartesian coordinate. Now for this one here, we have B1G to B1U in the acetylide orbitals. So those are the orbitals that we talked about in this question up here. This one was B1G, and I think the other one was B1U, I believe. B1G and B1U. But anyway, both of those are orbitals involving the ligand. So because they're both orbitals on the ligands, we would call this a ligand-center transition. For the term symbol, again, it's going to be only singlet states that are spin allowed. We just have to take the direct product of B1G times B1U. Now I don't have the direct product table here, but if you were to look that up, you would find that B1G times B1U is AU in this point group, so you give a singlet AU term symbol, and then to find if it's electrodipole allowed, we look at the AU Mulliken symbol, and we find that there are no basis sets, X, Y, or Z, or even quadratic ones either, that transform. So this AU term symbol would also be electric dipole forbidden. Alright, and then finally the last one here is from the dx squared minus y squared orbital to B2U. Oh, that was a dumb one, because dx squared minus y squared is empty. Alright, pretend like it's not empty. Sorry about that. Small typo there, but it's AG to B2U, but this time it's from a d orbital to a ligand orbital, so it's metal to ligand charge transfer. But again, if we just blindly follow the approach then to get the term symbol, it's going to be AG times B2U, totally symmetric times B2U, so that just gives us B2U back. So it would be a singlet B2U term symbol, and this time we find from the character table that B2U transforms as Y. So this would be a electric dipole allowed Y polarized transition. And so this would be lift dipole loud. Alright, so that's how we apply direct products to find the term symbol when you have a closed shell ground state, and then selection rules. Alright, this next one here deals with Tanabe-Scano diagrams, and I should have put the Tanabe-Scano diagrams in this presentation. I'll kick myself for not doing that. So I'm going to have to go to those, so give me a second here. Alright, we're back. So as I said, we're going to need Tanabe-Scano diagrams for this, so here we go. In this one, this first question asks about a D6 iron compound. So here we are with the D6 Tanabe-Scano diagram. Hopefully that shows up okay on your screen. I know the text is a little bit small on these diagrams. And so what we said is that it has an MLCT transition at 18,000 wave numbers, and the Rockoff parameter B is 900 wave numbers. And so what we want to know, and then say that dq over b is 2.5 for this first one here. Okay, so that's the situation here. We have an iron compound that has an MLCT transition of 18,000, Rockoff parameter of 900 wave numbers, and dq over b is 2.5. We want to know what are the DD states, the excited states that lie below this MLCT state, because the way that these charge transfer chromophores deactivate is through those lower lying DD states. So what we're going to do is we're going to first look at these first two terms here. So what this means is that the transition energy for the MLCT, E over B for that, is 18,000 divided by 900, which is 20. So our MLCT energy is right here at 20. I'll try my best to draw a straight line across, which may or may not look good. So that's our MLCT energy there, and we're saying initially that dq over b equals 2.5. So if we go up to 2.5, that's around there. And so I didn't draw that line very straight, so it'd be something more like this. Alright, and so we're looking for the three term symbols that are below that, so that's going to be these three dashed ones here, which are triplet T2, triplet T1, and then this one we follow up to quintet T2. So there's three term symbols that are below. This is our MLCT here at E over B equals 20. My line's not perfectly straight, but nonetheless, the three that are clearly below that are these three dashed ones here, which are quintet T2, triplet T2, and triplet T1. So if we'll go back and write those in. So those are the three that are below MLCT, and then Carol already wrote them in. But and then the next question is, how big would dq over b have to be to make sure that there are no DD states below that? So go back to the Tanabe-Scano diagram for this. We're looking for the situation where all the DD states are below this line here, which would help if it was straighter. Still not perfect, but close enough. And so what we want to find is the situation where all of the ligand field states are above E over B equals 20. So that's going to be where these two lines intersect. So that's approximately at about dq over b equals 3.5. And I gave you a little bit of leeway on that answer. I didn't, count it exactly, but 3.5 is probably the best answer. If you had at least anything bigger than 3, smaller than 4, I would probably have counted it. So as long as your answer wasn't way off. So 3.5 is the correct one there. And then, so that's going to be the two questions about that compound. Alright, and then if we go to the next one, we're still referring to this same compound. Let's say that this compound has 2 chloride ligands. I didn't give you the structure of it, but let's say 2 of the ligands are chloride. We want to know if we replace these chloride ligands with something else, which will increase dq over b. So we're basically looking for which of these ligands are stronger field. Stronger field ligands are going to be ones that would increase dq over b. That's how we would move to the right on that Tanabe-Scano diagram. So chloride is a pretty weak field ligand. It's a weak sigma donor and a reasonable pi donor, so both of those contribute to being weak field. So carbonyl and cyanide are clearly strong field pi acceptors. so is phosphine. If we compare to bromide and iodide, those are even weaker field than chloride because they're larger, meaning they have less sigma donor ability. So these would be the two that we shouldn't have put X's on. Fluoride, though, it's also a pi donor. It's also a halide, so it's not that much different than chloride. But because of its smaller size, it's a stronger sigma donor, which makes it a stronger field ligand. The field splitting will be larger for that. And then aqua is basically a sigma-only ligand or a very weak pi donor, but again, smaller than chloride, so typically stronger fields. So those would be the ones that you put X's by. The two larger halides are not stronger field than chloride. They're weaker field, but the rest of these would all be stronger field, meaning that they would all increase dq over b. Alright, sorry I keep pausing, but anyway, I'm back. Alright, so the next one is we have a cobalt-2 compound with the same MLCT energy and Raka parameter as the iron compound that we talked about before, and then dq over b is 3. What is the term symbol for the DD state that lies immediately below the MLCT state? So it's really the same type of approach as the other one. We're just going to use, and this time it's cobalt-2, so it's D7, so we're going to look at the D7 synonymous Coulomb diagram instead. Same MLCT energy, same B parameter, so it's going to have MLCT right here at E over B equals 20, and then dq over b equals 3. So there's only one DD state that's below MLCT, which is this quartet T1 here. So in this case with cobalt-2, you only have a single state to worry about that's going to be below, but it looks like it's going to be below at all values of dq over b. But it's going to be that single quartet T1 that lies below in the right side, the strong field side of the diagram. All right, so it's going to be quartet T1 for that one, or quartet T1G if we're talking about perfectly octahedral. All right, and then finally this last one here was one that most people got it right, but some of you I think try to make it more complicated than it was. We have an octahedral copper-2 complex, so this is a D9. It has a DD absorption band at 600 nanometers, which is 16,700 wave numbers. What is the value of delta O? Well, for D9 compounds, you only have one transition, which is EG to T2G, and that one transition has a frequency or an energy that's equal to delta O. So if you observe a transition at 16,700 wave numbers for a D9 compound, that means the delta O is exactly that value. So there was no math, no thinking, no dynamic Coulomb diagram involved because it's D9. It's just recognizing that relationship there. All right, last problem here deals with term symbols. So we have a metallic p block cation, polonium 2+, which can have very large spin orbit coupling. So PO2+ is going to be a P2 ion. Those are going to be the valence electrons. I guess it's probably what, 6p2, so whatever that row of the periodic table is, but it's P2 is the important part. And we want to know what the ground state term symbol is, ignoring the J value. So for a P2 configuration, if we want to find the ground state, we only need to consider the high spin terms, because so it's going to be P alpha 2, P beta 0 would be the highest spin. So if we use the partial terms for that, we go down here. So we have a P alpha 2, a P2 is a P partial term, and then a P0 is an S partial term. So it's going to be triplet states because there's two unpaired electrons, and it's going to be a P partial term for P2, S partial term for P0. P times S is just P, remember, multiplying by the S partial term does nothing, so that's going to be a triplet P. So triplet P would be the ground state term symbol. So there are other term symbols for the singlet states, but we only asked for the ground state here, so you only need to consider the high spin terms. We want to know what are the possible J values for this term symbol. So for a triplet P, 2S plus 1 equals 3, which means that S equals 1, and for a P term, L equals 1. When we find J values, remember that's going to be L plus S all the way down to L minus S. So L plus S is 2, L minus S is 0, and we also have then the number 1 in between. Anything in between those two would also be a valid J value. So the three possible J values are 2, 1, and 0. And then for which of these is the ground state? Remember that the ground state J value depends on whether it's going to be half filled or more than half filled. Less than half filled or more than half filled. So P2 is our configuration that's less than half filled. and so that means the smallest J value should be our ground state, which is 0. Alright. Then the very last question was, if we have, this was the only question on spin orbit coupling, the last topic that we covered on the very last day of class. We want to know if we have a J equals 2 term and it splits in an octahedral environment, what are the term symbols that result? So we said we may need to use the octahedral double group, but remember that the double group is only needed for half integer J values. J equals 2 is not half integer, it's an integer value. So for J equals 2, we can just use the regular O character table. We don't have to go to the double group. If you went to the double group, you'd still get the same answer, it's just more work. So if we just go to the O character table, then what we're going to do is we're going to apply these equations down here to get the character. This is a totally rotational point group, so we're only going to have this one and this one to consider, the identity and then the proper rotations that are part of this point group. We don't need R because we're not going to use the double group here, and we don't need these other ones as well for the purely rotational point group. So just identity and rotations. So we're going to apply these equations to J equals 2. So the J value is going to be 2, and then we're going to go for there, get the characters, and reduce it. So when we do that, for identity, 2J plus 1 is 5. For the rotations, for C3, theta is going to be 120 degrees, or 2 pi over 3. And then J equals 2 plugged into this equation along with that. So we should get a character of minus 1 for C3. For C2s, we have two different classes of C2s, which will give the same character because this equation only depends on the angle of rotation, not the direction. So J equals 2, theta equals 180 degrees, or pi. So for the C2s, we get characters of 1. And then for C2, we're going to use a theta value of 90 degrees, or pi over 2. And so when we put those in and do the math, we get a minus 1. So those are the characters we get, and then we just need to reduce this representation, which is going to be E plus T2, or if you chose to use the double group and go with the other alternative notation, gamma 3 plus gamma 5, or there could be some alternative mulligan symbols for the double group as well that I would have counted. But in the regular O point group, it's just going to be E and T2. And again, it's just applying these equations and reducing. Alright, so I went through that kind of quickly because I didn't want to make a video that took forever for you guys to get through or forever for me to make. So if you have any additional questions about the final exam, feel free to ask me. Unfortunately, I don't think this material is going to be very important for the courses you guys are taking next semester, most likely. But some of it might come up from time to time, and also in your research it might be important. So hopefully we're clear on all this, and hopefully you got some benefit from this last video. Alright, so I'll see you guys later on, and have a good break.